Welcome back to the Microchip series on integrated op-amp peripherals. This video in the series will focus on the development tools to simulate, then set up the op-amp peripheral in the new PIC18Q41 and AVR-DB product families. Microchip offers a free analog circuit simulator called MINDI to let customers simulate their analog designs before prototyping. MINDI is compatible with both the integrated op-amps in the PIC18Q41 and AVR-DB product family, as well as a selection of discrete amplifiers that Microchip produces. After downloading and installing MINDI, you may need to add the integrated op-amp models into the tool. This video will show these steps, however future versions of MINDI will have these models pre-installed. After simulating the integrated op-amp circuit, I will show you how to use the graphical code generators, MPLAB code configurator, and START를 to create the required APIs to implement the op-amp circuit on the device. You can find a link to these tools in the video description. This section of the video will cover installation of the MINDI models. If the models are already installed in MINDI, then you may skip these directions. First, download the models from the link in the video description. After unzipping, there are two folders, encrypted and unencrypted. The encrypted model is functionally the same as the unencrypted model, however, MINDI uses fewer software nodes when simulating it. This enables more complex circuits to be simulated in the software. If you're planning to use another SPICE simulator, the unencrypted model should be installed. Installing the model into MINDI is as easy as drag and drop. Open the downloaded folder with the encrypted model. Drag the desired model into the command shell on the left side of the screen. Click OK to install the model. And that's it, the model is now installed into MINDI. To test the performance of the op-amp we just installed, let's create a simple non-inverting amplifier circuit with a gain of 2. I'm going to create a new blank schematic, then I'm going to insert an op-amp from the toolbar. Then I will right-click on the model to change it to the model we just installed. The integrated op-amp models are classified by MINDI as a microcontroller peripheral. For this video, I'll be using the PIC18Q41 model, which is identical to the model used for the AVR-DB. As the op-amp is in the microcontroller, it is a single supply device. I will assume the device is running at 5 volts. I created two voltage sources, one to create a supply rail of 5 volts for the op-amp and the other to be used as an input. Next, we need to add the resistors for feedback. The internal resistors on the device have a nominal resistance of 20K per unit, and a gain of 2 uses 8 units for both R1 and R2. Now I'm going to add the ground reference points to the circuit. With all parts in the circuit, I need to wire them together. In MINDI, clicking on a node will automatically start a connection. To finish the connection, I just need to click on the destination node. I can right-click or hit escape to exit this mode. Once everything is wired together, I will insert the voltage probe points by going to the Place menu, Probe, then Voltage Probe. Alternatively, you can hit the B key. After placing the probes, right-click on them and press Edit Part to set the properties, such as the label or the analysis they are associated with. Now let's configure the signal source. The input signal is a sine wave at 1 kHz that has an amplitude of 2 volts and a DC offset of 1 volt. The last step is to complete the analysis. I'm going to run a transient analysis of 1 millisecond. At the cost of computation time, you can use the Advanced Options menu to reduce the maximum time step in Simulator at the cost of performance. After all this is set, I can click the Run button here or the Play button on the schematic page to see the result. For reference, here's what the output looks like on a PIC18Q41 and AVR-DB device. As mentioned earlier, MPLAB code configurator and START are graphical tools that can generate the initialization code and APIs to control the peripherals on the device. For MPLAB code configurator, first open MPLAB X and create a new project. I'm using a PIC18F16Q41 device. I name the project and select the XCA compiler as my toolchain. On the top of the screen is a button to launch code configurator. Before setting up any device peripherals, I'm going to set up the microcontroller to use the high-frequency internal oscillator at 8 MHz. Then, on the right side, I'm going to select the OPA, or Operational Amplifier, to design. I'm going to set the charge pump to on, the configuration to a non-inverting amplifier, and then change the resistor ratio to a gain of 2. If I need to switch pin assignments with the external signal, I will need to do so by clicking on the pin table below. I am going to press the Generate button, which will generate the main function, the software API, and the initialization code. After compiling the generated code, the device is now ready for programming. This configuration was used to generate the waveform shown when comparing to the MINDI simulation. Finally, I will show you how to set up the AVR-DB's op-amps in START, which is linked below. I'm going to start by creating a new project. For the device, I'm going to use the AVR-DB Nano. By selecting the Nano, START will label the pins connected to the circuits on the Nano, such as the push button and the LED. Now I am going to add an operational amplifier peripheral by searching in the box. The AVR-DB has up to 3 op-amps on board. For this demo, I'm only going to be using 1 op-amp. The op-amps will be run in single mode. I'm going to change the op-amp config on op-amp 0 to the non-inverting amplifier. Now I will change the gain of the internal resistor ladder to get a gain of 2. With everything set up, I can now export the configuration to my IDE of choice. As shown in this video, the software development tools associated with the integrated op-amps accelerate signal chain development. While simulation tools, such as MPLAB MINDI, cannot capture every edge case or parasitic parameter, they are an invaluable tool for testing and evaluating analog circuits. MPLAB Code Configurator and @mouse_start also fit into this design flow by automatically creating the APIs and initialization code for the microcontroller peripherals, including the integrated op-amps. Thank you to all the viewers for watching this video. You can find development tools and products are linked in the video description. If you enjoyed this content and found it interesting, please like and subscribe.